So in the previous video we have done the simulation in the custom compiler. This is my CMOS inverter where PMOS transistor and MOS transistor connected with the input, and now we do the simulation once again. And in this video mainly we concentrate on doing the analysis in the better way, where let me go with the simulation once again. Prime wave. Yes, so there is a option that we can add the analysis and we can do all the things here. We can add the inputs and outputs to view and setup, where we have to add the model files. And instead of doing all the things again, there is an option that we can load the previous state, right? So where open access the particular cell which was there already, give enter, so that whatever the previous state where up to which we have done, right, we can reopen it again. The same state we can reopen it again. So in the same way, if you do some other steps here, right, let us suppose I added the transient start time step 1 nano and stop time 100 nano, for suppose I added another analysis also. So now I just wanted to close it right now, and just I wanted to open it after 1 hour, right? So instead of closing directly, there is an option that we can save the state, and after 1 hour, right, whenever you wanted to continue this. Yes, so let us continue the same work. For that, what we do is, there is options like a session. We can save the state and we can load the state it afterwards. So whenever you wanted to continue the work, you can load the state. Whenever you wanted to stop the work, you can save the state. So now what I do is, I'll just remove this once again, and operating point we make sure that we have to keep it in all and give it OK. And now transient, first let me check whether the functionality of the circuit is correct. Control R, right, there is a shortcut for doing the simulation. Run the simulation, Control R. C1 defined because like we have the variable over there across the capacitor, so that variable name is not defined here, sorry. And variable name, edit variable name, so take it from the schematic and give the capacitance value 0.01 picofarad and give it OK, and now do run. Sorry, model files were wrongly selected. Instead of 14 I selected 32, so that was the problem. So that's why it was not done. Now we'll go with transient analysis once again, and this capacitance value, let me keep it to C value small, means it takes very low time, like yes, give it's okay, right, control run. Yes, so this is how I get ungroup. 1 means 0, 0 means 1. For the opposite values, that I get it as per the specification. So inverter specification as 1, it has to generate a 0. For given 0, it has to generate 1. So the functionality as per the transient analysis is checked. And now let us check that operating point once. Let me select operating point, input and output waveforms across the operating point. Let me select operating point, and let me do run. Control R is the shortcut, let me use it again. Yes, so simulation done, right, finished. The simulation finished, and after that what I do is, I'll go with the results, print DC node voltages. Let me select. So the DC node voltage of this one, I can get it over here when the given input is A equal to 0, and I'll click on this one. I'll get the Y value is 1.1, and the VCC value 1.1 is supplied, and the ground value is at a 0 level. So like that, if it is a complex circuit, So at each and every node voltage I can monitor it over here. I can monitor it over here with this option. So let me repeat the same option. Where we get it is, we have to go with the results and print the DC node voltages, and operating point report also we can get it. You just click over here and we can get that operating point also. So this is the operating point where MOS transistors, where it is operated, and capacitance value, current and power, and all these things we can get it. Print the DC operating point. The transistor, if I select, so I'll get yes, I'm not getting. So I can get annotations also. Sorry, this one operating point means if I click on this particular transistor, it has to show, but it's not showing. Like I'll show it again. So coming to annotations, results, annotate, and the DC node voltages, and the simulation DC operating point, where I can get the simulations also. Yes. So coming to the simulation, when I do the simulation across the operating point and transient analysis both, so let us go with the operating point once. So the transient analysis, we have to select it to verify the functionality. That's what we have done. Now we'll go with the operating point and check the conditions of the each transistor. So let me click on the operating point, and there must be a format in all. If you keep it in another format, right, whatever the notations you are expecting you will not get. Just keep it in all, and just use Ctrl R, run the simulation once. After simulation is totally finished, then you go with the simulator once, and there you have to go with the results and print DC node voltages. So whatever the value across the node voltage we wanted to measure, right, we have to select the particular branch or node. So you can see that the voltage across the particular node or voltage across the particular branch. So similarly you have to select like how many branches that you want. This branch is with the 1.1, given 0, then you will be getting logic 1. Logic 0 means we are getting logic 1, right? Exactly, inverting operation, right? The functionality, even you can check it like that. Instead of transient analysis, even you can check the functionality across the circuit also with these notations. And is that 0 potential is applied over here at the pull down, and is the VDD is supplied at 1.1 level. So is the circuit is taking total voltage supply and the total at the ground level it is there or not, we can check it across this one and give it OK, right? In the similar way, I have another option, right? Go to results once again, print operating point report and operating points also. DC operating points means you can select that particular transistor, and you can see that what will be the parameters of that particular transistor at DC level. So there will be a VBS is 0 because like body terminal and source terminal is connected together, threshold voltage of this much, and the gate to drain capacitance of this much current is conducted, and the capacitance of this much, and all the GM values also you can see it across the transistor. In similar way, right, if I can select on this one, right, I can even see the parameters of the M16 transistor also. So with these values we can do some calculations, and where we can do the analysis in the better way, right? So in the similar way, there is another option also all together. Right now in the print you can see that operating point report also. Report means everything will be shown as a report here. If the MOS transistors means, right, there are two transistors, M16 and M17, right? Let me show it again. M16, M16, right, M16 and M17. M16 is the NMOS transistor, right. M16 is the NMOS transistor, M16 is the NMOS transistor, this is the NMOS transistor, this is the PMOS transistor. As the input is 0, you can see that the analysis operating point at t is equal to 0 it will show, and the NPN transistor, sorry, NMOS transistor, it is supplied with VD, VGS is 0. For NMOS transistor, once it is VGS equal to 0, it will be cut off. It will be in cutoff. In the previous video we discussed this one also. So region 0, it is nothing but cutoff. Region 1, region 2. So this is how it will show the indication, region 1 and region 2 and region 3. So when it is in the region 1, it is the indication of the transistor there in the cutoff. Similarly, if it is 1, it is in the linear. If it is a 2, it is in the saturation. If it is in the 3, subthreshold. So this is how that each region notations that we have to remember. Now you can see that the transistor, when it is in the VGS value equal to 0, the transistor, as we know that NMOS transistor is turned off, it is going to be given with the indication of the region 0. So in the similar way, it is giving the indication of region 1 means the transistor, when it is in the one region, it is nothing but linear, so it is turned on. So means when you give the logic 0 at the DC condition of 0 at the time 0 at initial time, right? So DC input 0, once it is applied, this transistor will be in linear, this transistor will be in the cutoff. So that is what in the report it is showing, right? From the report we can do the analysis with the values where it is going to be printed. So net values also printed, this all capacitance value also printed, all the values we can take a note and we can do some calculations, right? So this is how we have the option over here, right? Operating point results, we can use it in the similar way. Right, in the similar way, I can even see that another annotations, right? This is the print option where we use these three. So annotations also very useful, right? When we go with the DC node voltages, so if you click on this one, the DC voltages of the particular branches will be displayed there itself. So 0 will be the input is connected at the gate terminal, 1.1 it is going to be taken as a supply, that 1.1 it will be driven to the load. The similar way, this 0 will be the input, 1.1 it is the supply, because this transistor is turned off, so 1.1 will not commit over here, so it will be at 0 level, right? So this transistor is turned off, this transistor is turned on, the voltage notations you can see it here. And in the similar way I can get the another annotations also, DC operating point also. So I can see that all the annotations, previously we have seen all these values on the report, now the same values, right? All the values we can see it on the display itself, right? The transistor with this all annotations will get it, all the annotations we get it. And now we in this annotation, right, we have all the values, but we don't know the region of operation. Now what we do is, so we can even see the region of operation for the transistor, because like in few cases when the circuit is very complex, when we need a region of operation, if it is identified to the particular transistor, we can change the biasing so that we can bring the functionality of the circuit into the existence. So now what we do is that we can go with the annotations and select that advanced and give apply. So now as per the notations here, it is showing that this is in linear, means when it is in blue color, right, it is in the linear region, red color means it is in cutoff, right? So as the notations you can see it, this transistor is in the cutoff, this transistor is in the linear. So that is what the same thing happening when the 0 is the input is applied, this transistor is linear, so that 1.1 will be conducted over here, the maximum current will conducted over here, the capacitor will be charged to the level of 1.1. so this transistor is because turned off, so there is no chance that capacitor will be discharged. So 0 is the input, 1 we will be getting the output as per the functionality because of the particular region of operations that particular transistor has, right? So this will be the notations very important over there when you do the analysis. The similar way when the transistor is functioning, right, I just wanted to see the transistor notations even it is in the transient mode, means when that not at 0, when you wanted to see at some other case, let us suppose 93 nanoseconds. At 93 nanoseconds I wanted to check the functionality. So now let me run the functionality, let me simulate it, so ungroup. So at 93 what happening, input is at a high level, output is at low level, right? So as of now we just observed that the transistor input is low, output will be high. That is the case we observed at a DC level at 0. Now when we go with the transient analysis, when at 93 nanoseconds at which, so what will be the functionality and what will be the regions of operation for the each transistor, we wanted to check it once. The similar way what we do, we will do the same step it again and print the node voltages. Print the transient node voltages. So at 93 you want, right, 93 nanoseconds, right? So I can see that 93 nanoseconds, right, what will be the value of the input is 1.1. at 93 nanoseconds it will be given with 1.1 as we observed, and now this one will be low. So when it is given high, it is going to be generated low. That's what you can print it over here. So in other nodes also you can take the same print in the same sheet itself. That option is still there, the print and the transient node voltage, transient operating point also. At 93 you can click on that particular transistor. At 93 you can see that all the all the parameters of the transistor here, right? So that is how we can take the reports at a particular time, whatever the time at which that response of the circuit you can verify it. So similarly we can go with the annotations, right? Advanced annotations will do it once, and instead of DC, right, I select the transient at 93 nanoseconds. I will want to verify it once and give it OK. So now if you see this one, now if you see this one, the red color is this one, right? It is in now cutoff because like you give that 1.1 voltage over here. So at 93 nanoseconds you are giving like a 1.1 voltage. So for 1.1 voltage this transistor, PMOS transistor, will be cut off, so it will be in a red color. So this transistor will be in linear. So what happening for the given high voltage, right, this transistor now it will be conducting whatever the capacitor it has a total charge of 1.1 previously, it is going to be discharged right now. So this capacitor will be now hold with the charge of 0, so output will be 0. So input when it is applied high, output will be becoming low because of the notations across the transistor. This is how the annotations use to make the analysis easy by taking the print on the schematic with the notations with these colors. For the simple circuit it is easy, that it will not be much important, but if it is a complex circuit it is very useful where like knowing the region of operations across the complex circuit where it has multiple transistors.